Hey, math people, we're looking at linearization today, which is our fifth lecture through the contextual applications of differentiation chapter in Calculus 1. So what we're going to do is we're going to connect it to the tangent line right away because it's more or less the tangent line. We'll look at it graphically, understand how it connects to over and underestimations and how it curves, and then just look at some examples. This video is for you, Maya, so make sure you use the timestamps. You pause when you need to. Use this video for you. Be patient with yourself, and let's do some math. So how do you find the equation of a tangent line? Just starting with that right off the bat. 3, 2, 1. You know how it goes. It's just point slope. You plug in your derivative evaluated at your desired value for m. Desired x value is just your x1. And then calculate the function at that desired x value for your y1. Okay, so here's how we define linear approximations. It's just a tangent line. So within a local domain of some a, so x equal to a, on f of x, a tangent line is a pretty close approximation for evaluating nearby values. This has everything to do with local linearity. So if I were to graph, I don't know, let's look at x squared, right? So we'll just look at x squared. If I were to graph the tangent line at 1, that would be 2 times x minus 1 and then plus 1, right? So if you were to zoom in a whole lot, you see how these are pretty much the same thing, right? I can't distinguish a difference here. So nearby values to 1, 1 are really good approximations. But of course, as you zoom out, they become worse and worse approximations to a point where they're indistinguishable. So it's only really for close values we can follow this process of f of x being approximately equal to the linearization, we call it, which is just the tangent line nearby a. So how can you tell if a linear approximation is an over or underestimate? Has everything to do with how it curves. So if you could just kind of like envision a bunch of lines within this curve, right? Envision a bunch of tangent lines just everywhere, really. And then, yeah, the idea will come out if you think in respect to, I don't want to give it away. So see if you can just come up with this first, and then I'll give you a hint. 3, 2, 1. Okay, so the hint is with relation to concavity. So something if you're concaving up, something if you're concaving down. All right, 3, 2, 1. So here it is. If you were to just draw a bunch of tangent lines on this left side here, you would see that all the tangent lines are above the curve. Well, the curve is concaving down in this moment. So we'd say that if the second derivative, we'll do the overestimate one first, right, is less than 0, then your linearization will be an overestimate. When you're concaving up, every single one of these moments is always below, and every single one of these tangent lines is always below the curve. So if double prime, f double prime is greater than 0, so you're concaving up, then your tangent line will be an underestimation. So it kind of flip-flops. You're an overestimate when you're concaving down, underestimate when you're concave up. Aight, so let's just give it a go. So use the tangent line to approximate f of 0.1. Is it an over or underestimate? So what you're going to want to do here is this. Find the tangent line at the nearest integer value to whatever you're trying to approximate. So in this case, 0. Find the tangent line at 0. Then find its concavity within that interval from 0 to 0.1. So if it's concaving up during that time, then it would be an underestimate. If it's concaving down, it's an over. Let's give it a go. 3, 2, 1. So I went ahead, I found the tangent line. I found it to be 1 times x minus 0 and then plus 4. I just did first derivative, plugged in 0, and then plugged in 0 into the OG, and then I saw this is my function. Okay, so I would say that f of 0.1 is approximately equal to L of 0.1, which if I were to plug in 0.1 here, that would just be 4.1. Now let's think here, is this an over or underestimate? Well, f double prime is 2x minus 6. At 0, in that like interval, I would say between 0 and 0.1, we would notice that our output is negative, right? Yeah, so it's like negative 6-ish. So we're going to be concaving down in that interval, so therefore it would be an overestimate. That tangent line would fall above the curve. Let's see if you can try this with these two now. So follow the ebb flow. So I would say really try to pencil paper on this one. Give this a go. So find your nearby x values to the desired inputs that you're trying to approximate, right? Consider how, like, if you were to plug in an 8.8 here, that would just take like a long time. You know, just imagine if you were stranded on an island and you needed to approximate 8.8 here. There's no way that you would sit and cube 8.8, would you? You would instead, of course, use the tangent lines. A little goofy of a scenario, but let's kind of just talk about how there is utility to this. If you have some sort of program that you're really just interested in some like approximations, and it's just like a very long equation to churn through, that would take a lot of computation power that you maybe need to run through it many times over. Sometimes an approximation is not too bad. It could save you some computation time and power, right? Energy. Anyway, give these next two a go. Find that nearby value, find the tangent line of that nearby value, and then plug in your 8.8 and 2.7 into that linearization. State if it's an over or underestimate. 3, 2, 1. So looking at all of these, I ended up getting the following tangent line at 9, which is nearby 8.8. And then if I plug in that 8.8, I would have got 7.4 as the approximation. Again, the function second derivative is 2x minus 6. So if you were to plug in like 9 here, that is positive. So this is an underestimate because it's concaving up, so that tangent line is going to be below the curve. And then for this last one at 2.7, if you consider the tangent line at like 3-ish, that would be concaving. That would be concaving down, right? Oh, this one's a little tricky. Yeah, because we're at, this one was very tricky. We're on the left side, right? Because at 3 is the point of inflection. So this was intentional. I was wondering why I had another overestimate here. But since we're approximating at 2.7, that's on the left side of 3. So you're kind of coming up with like, you're using this tangent line. And if we're on the left side, actually I think this is also the curve. If we're on the left side, it's going to be that overestimate, right? If you were to plug in 2.7 into this, that would be negative, so overestimation. So so here we're finding the point of inflection, literally, or the tangent line, literally at the point of inflection. But since we're, at 2.7 is on the left side of it, we're a part of the concave down interval. So overestimate, a little tricky there. All right, so for the next two, I want to approximate what these values may be. 4.15 squared, and then the square root of 8.9. So think about what functions in play for both of these. This is just x squared, and this is just square root of x. So I want to come up with the tangent line at its nearby value. So what's nearby 4.15 and what's nearby 8.9? And then utilize that second derivative to determine if it's an over or underestimate. All right, so give these a go. 3, 2, 1. So I have my x squared function, and I'm coming up with the tangent line at 4, right? So I went ahead, I got 8 times x minus 4 plus 16. So when I plug in my 4.15 into that, I'm getting 17.2, and I'm thinking, well, okay, x squared is always concave up. So because of that, this must be an underestimate. Whereas with the square root of x, that's always concave down, right? I don't have to actually solve out these derivatives, right, to know that x squared is always concave up, and then that the square root of x, now it follows more that concave down shape to it. I don't actually have to compute them. I just need to know the curvature of it all. So I found the tangent line of the square root of x. I ended up getting this linearization here. And as I plug in 8.9 into this linearization, I get this value. So since it's concaving down, it's going to be an overestimate. The tangent line's above the curve. Okay. So for 4, it's known that we have some twice differentiable function, and then we have all these little tidbits of information. We know f of 1 is 2, we know f prime of 1 is 3, and then we know it's concaving down. So use linearization to approximate f of 1.23. So it's just giving you all the information. This one's just going to be pretty plug and play into tangent line, and then utilize the fact that f double prime is less than 0 to figure out if it's over or under. So this one's kind of all laid out nicely for you. Sometimes it could be given to you in through table or tabular information. Here I'm just explicitly giving you all the needed expressions within the prompt. So 3, 2, 1. Tangent line, I'm just using that slope of 3. I'm just using that input of 1, which is nearby 1.23. And then I'm using that output of 2 for your y1. So when I approximate the 1.23, I'm getting 2.69. And then, of course, it's an overestimate. We're given explicitly that it's concave down. So tangent line will be above the curve. All right, and then just two general scenarios. If you have some sort of exponential where your base is greater than 0, or some sort of log where your base is greater than 1, what will always happen with your linear approximations in both of these scenarios is an overestimate or an underestimate. I'm not even giving you where we're coming up with these linear approximations. I'm just asking it in the general sense because there is something particular about the shapes of both of these graphs that would render them to always have a particular answer. Let's see if you can find it. 3, 2, 1. So yeah, an exponential always concaves up, right? We can just even graph that if we really wanted to. No matter how you swing it, there it is. You're always fitting this U-shaped mold. You'll see here that for these log graphs, these are always concaving down. So always, always, always concaving down. You always have that more N shape to it than U shape. And if you don't trust me, fine, take the second derivative. You'll see for yourself. Okay, the last little section here. So approximate the sine of a small angle. What? What does that mean? So consider an angle near 0. So come up with the tangent line or linearization formula for sine of x when we're near 0. And then use what's called the small angle formula for that you're going to find above, the approximation of sine of 0.1. So is this going to be an overestimate or an underestimate? Let's see. So right now you're going to find the tangent line at 0 for sine of x. 3, 2, 1. Not a bad one, right? Take the derivative, it's cosine. You plug in that 0, you get 1 as your slope. And then since we're near 0, small angles, right, are near 0, that's going to be my x1, and then my y1, well, 0, comma 0 is just going to be 0. So yeah, sine of x is approximately x, right? I can go ahead and graph these, and of course, they're not the same. We know that. We know these aren't the same. But what if I was a super tiny creature, and I was just really close to 0? To me, they look the same if I'm a small creature, right? But alas, different. Okay, so if I were to plug in 0.1, well then, the angle is approximately going to shoot out that ratio of opposite over hypotenuse of 0.1. Of course, this is going to then be an overestimate on the right side because we're above, and then on the left side it would have been negative below. There is, here's my rendition, calculus in the humming of strings, little small sine waves, right? Pythagoras originally said it. That's my little tweak. Okay, that's it for this one. Math on.